Hey everyone, in this video we're going to continue talking about logical thinking by introducing what are called the three laws of thought. Now chances are you probably thought about and maybe even come to these same conclusions here, and in this case this video will simply state what many consider to be obvious. However, these three laws lay down the foundation for rational thought in what is defined as logic, at least in the Western tradition, and these ideas can be traced back over 2,500 years to Aristotle and some of the thinkers around the ancient Greek time. So let me talk about the three basic laws of thought. The first is the law of non-contradiction, or the LNC, which says that a thing cannot be and not be in the same way and same respect at the same time. Put another way, a proposition cannot be both true and false. It can only be exclusively one or the other. For instance, the proposition Magnum XL 200 at Cedar Point is over 200 feet tall cannot be both true and false. If it could, then this would mean the ride is both greater than 200 feet tall and less than or equal to 200 feet at the same time. And we would often say, this is absurd, this cannot be. Now, some people may say, well, what about the proposition that Magnum XL 200 is red? Isn't it both red and white? And sure, but what we mean by red here isn't necessarily red all over. We just mean that, say, maybe the track color is red, which isn't incompatible with the supports being gray or white. What the law of non-contradiction would forbid us saying is that Magnum XL 200 at Cedar Point is both red and not red once we are clear what we mean about red. The idea here is if there is any ambiguity, you can eventually break this down into what are called atomic statements that are clearly true or false. And symbolically, we can write the law of non-contradiction as not quantity A and not A. And later on, we'll clarify what these symbols mean and everything. And this is contrasted with some Eastern ways of thinking, which can be more dialetheistic, meaning you can have statements that are both true and false. You see this way of thinking a bit more in some Buddhist and Indian schools of thought, but not as much in the West due to the influence of Aristotle and, of course, the Christian tradition. And one of the areas in which it makes a lot of sense not to allow contradictions is in designing circuits, where transistors behave as switches, which are either on or off, but not both. In electrical engineering, we may argue that the law of non-contradiction is a physical necessity in addition to a sort of logical law. For instance, we would say a transistor cannot be both passing current and non-passing current at the same time. For mathematics, we also do not permit contradictions. And for this introduction to logical thinking, and mainly for the sake of scope and time, we're not going to be exploring pair-consistent logic or anything that permits contradictions. The second law of thought is the law of the excluded middle, or the LEM. In Shakespeare's play Hamlet, the eponymous character Hamlet famously says, "To be or not to be, that is the question." And this is the famous law of the excluded middle, which says that things are either true or false. There is no in-between or middle where things are somewhat true or somewhat false or neither. At bottom, in Western logic at least, propositions are either true or false. Now, there may be some cases where we don't know whether a certain proposition is true or false, but Western logic says that all well-defined propositions do have a truth value, and this distinction between what we know and what actually is. Put another way, a proposition cannot be anything other than true or false, and combined with the above, cannot be both either. This is how we would write it symbolically. We would say A or not A. And lastly, we have what is called the law of identity, which simply just says things are equal to themselves. If I have an item, say a human, then I can affirm that a human is a human. Symbolically, we may write it as for all x, x equals x. There's not really too much to say about this, though it will come up when we break down more complex statements and eventually get something like A equals A, and we can say this is true, this is a tautology, meaning it's true. And for those of us in the West, these three laws seem pretty trivial and basic. However, one of my goals here, along with these videos, is to help your thinking become more rigorous, and this often involves spelling out these things and writing them with all the different rules and possibilities. Now, as you'll see later, this really helps simplify things, as each proposition can only take one of true values, and everything is, well-defined and behaves nicely. However, is this too simple? What about cases where we don't know whether a proposition is true or not? Well, there's a big distinction between whether a proposition is true and whether or not we know it is true. This is a distinction between ontology, the study of what is, and epistemology, the study of knowledge or what we know. And propositions are true or false, though we may not know whether a proposition is true or false at a given time. For instance, consider the claim of whether there are an even number of atoms in the universe, or an alternative claim, there are an odd number of atoms in the universe. They both can't be true, and there seems like there would be a right answer to this, but we would never know the answer unless I guess we counted them all up. There are some cases where it makes sense to represent logic with what are called fuzzy states or things that don't have clear cutoffs. And consider temperature. There may be times the word warm is better than the word hot, or maybe times where both warm and hot are appropriate. In these cases, what we often try to do is break these things down in a way where our proposition is well defined enough so we can say something about it. For instance, things like temperature that may have a matter of degree, we can still make propositions that are true or false about them by talking about, say, maybe ranges, like is the temperature greater than 200 degrees Fahrenheit? Or what we can do is represent things with numbers and do this with quite a bit of precision, even if we only restrict ourselves to true and falses, to zeros and ones. With enough zeros and ones, we can represent a lot of different numeric values, and we can build up very large and very small numbers. And my point here is to say that even if things in the real world seems to be matters of degree, the logic of assigning truth and falsity to things can still be applied to them and can be applied with pretty much arbitrary precision. Now, what about cases where there are things like the logic going from low to high, and there's kind of this middle ground or undefined region? Doesn't this kind of contradict our idea of the law of the excluded middle? Well, one of the things we can do is we can represent this in our true-false on-off system as logic. And once again, this on-off system is often called Boolean logic or binary logic. And what we can do is have two bits or two propositions. One being whether the voltage is well defined at a given point in time, and two, if it is well defined, this other proposition, whether or not it is high or low. And in this way, we can, even with fuzzy things, analyzing them and using binary or propositional logic to understand them, there's still an application here. So hopefully what I've done here is giving you a reason to think that, it's still useful to understand and study binary logic, even if there are things that may not seem to conform to it on the surface. And for a fun thought experiment, think about how the law of non-contradiction and the law of the excluded middle can be combined with a single logical rule. It is possible to combine these and with a single logical connective, write them both at the same time. So think about what that connective would be, and you could let me know in the comments if you think you figured it out. And anyway, thanks for watching, and I will see you in the next video.